OK, so I wanted to just briefly give a case study here of one of the more interesting modern-day VLIW architectures, or probably the most famous and possibly also the most infamous VLIW processor out there. This is the Intel Itanium, also known as the Intel IA64, or what's known as an EPIC processor, explicitly parallel instruction computing architecture. And a lot of this work actually was done in collaboration between Intel and HP. HP uses these a lot in their big servers. They're sort of big mainframe, well, not quite mainframes, but big, heavy, big iron computers. And Intel was trying to use this to effectively kill all of the other workstation vendors. And this was going to be their 64-bit solution to computing. So it's a modern, non-classical VLIW. And this was going to be Intel's chosen ISA. They were going to deprecate x86 and choose IA64 as the 64-bit ISA. And as we now know, going a few years forward after the creation of all this stuff, that didn't really happen. Intel went and did this. It built a bunch of processors with this instruction set. You can still buy processors with this instruction set, but it never got as good of acceptance as the competitor. The competitor is what at the time was called AMD 64, which is a 64-bit extension to what people already had. And that's what people ended up wanting. It's just a 64-bit extension to what we already had versus something totally different. OK, so a couple features here. It's an object code compatible VLIW. So it's not quite a VLIW in a classical sense. It's object code compatible, which means different generations, different microarchitectures of this VLIW can have the same instruction code and the same binaries, and you don't have to recompile. And how they did this is effectively, as I alluded to before, they had the ability to have parallelism straddle across instruction bundles. And they had this notion of groups, which we'll talk about in a second. So first few implementations of this, Merced was the first Intel Itanium implementation. It's kind of like the 8086 for x86. But Merced, as lots of things, you'll realize if you look at Intel code words and Intel code names, named after a river. Intel likes to name their things after either rivers or places. I think this has something to do with you can't trademark a place name, so they just sort of get around that and make sure they don't have any trademark issues by choosing place names for all their code names. One of the big problems here, it was supposed to ship in 1997. First customer shipment, not until 2001. It's a 4-year miss. And superscalars and other things had caught up on it at that time. And it was supposed to be faster and better than everything else. And the first one was not very good. It had low clock rates and was not as high performance as it was supposed to be. And sort of the x86 side of Intel's business line actually had almost the same performance as the first Itanium, and then very quickly surpassed the first Itanium. So their high-end processor wasn't actually very high-end. Couple other things here. So McKinley was the second implementation, shipped pretty quickly after that. This was much better implementation, but it's still hard to do. But we're still building these things. So in 2011 at ISSCC, Intel introduced the Polson processor. Big machine here. 8 cores and 32 nanometer. Lots and lots of RAM. We'll look at that. Yeah. So 32 megabytes of shared L3 cache. Big processor. 544 square millimeters in 32 nanometer. So at the time this came out, this was the biggest processor ever built. Most number of transistors, so over 3 billion transistors. Or at least the biggest commercial thing. Intel might have had a research prototype, I think, that might have had more transistors than this. I think their multi-core processor, or their, what do they call it, the SCC, their single chip cloud computer might have had more, but I don't actually know the transistor count. But from a commercial processor perspective, huge chip. But they're selling it into extremely expensive sort of sockets. They're selling this chip for a premium. It's going into big mainframes. That was not where this was originally destined for. It was destined for both big mainframes and workstations. But now this is sort of the, in 2012, standing here now, this is not used in lots of other places except for sort of bigger hardware mainframe sort of things. So a few interesting things here is the cores are multi-threaded, and you can execute 6 instructions, or you can fetch 6 instructions per cycle, and you can execute up to 12 instructions per cycle per core, and then there's 8 cores. So this is a beast of a machine, very, very high performance computer. Okay, so let's dive into some of the details here of Itanium. Itanium has a 128-bit instruction bundle. And inside of there, you can fit the 3 operations. And then there's some what are called template bits, which sort of says what is in the instruction bundle. So it's not actually a fixed format bundle. These instruction boundaries can move around a little bit. And they did that so you can sort of mix in something like a immediate instruction with an instruction which doesn't have immediate, and get more space in the bundle for the immediate bits. So you can have, or branch offset or something like that. These template bits also describe how a particular bundle relates to other bundles around it. So sometimes these are called begin and end bits or start and stop bits. So it says the number of instructions which can execute explicitly in parallel. And the machine doesn't necessarily have to execute these in parallel. So for instance, if you say 20 instructions can execute, or 20 operations can execute in parallel, but your machine's only 2 wide, or they build a 2 wide implementation of Itanium or IA64, you just are going to execute 2 wide for 10 cycles or something like that. But what's really cool here is the compiler is able, just like all the other VLIWs, to express the parallelism to the machine explicitly. Some interesting things about the registers. Because this is a VLIW processor, and because you're going to have to do code scheduling like what we saw in last class, and that increases the general purpose register pressure. You don't have a register renamer. So you can't go and use different names for things, and the hardware is not going to rename things for you. So instead, the compiler and the software is going to have to do the renaming. So they had 128 general purpose registers and another 128 floating point registers. And they also had these predicate registers. So they're not quite full predication, but they're pretty close to full predication. So you can have bits that say whether later instructions are going to execute or not, and you have to compute that into a little register file. So they had a predicate register file that you have to bypass. So that's sort of interesting to see. And then they had a really interesting feature here, which is called rotating register file. And let's talk about what a rotating register file is. So the problem this is trying to solve is in a code sequence as we saw in last lecture. If you have a very long instruction word scheduled piece of code, and you want to get good performance, you're going to have to unroll the loop, and then you have to software pipeline the loop. But when you do this, this is going to increase your register pressure or increase your register names, how many register names you need to use. And as we saw, you're going to have to add extra special code in the prologue and the epilogue, which are different than the main loop body. So how do you solve this in one fell swoop? Well, you add a subset of your register space, which will sort of statically rename itself every loop iteration. So it'll slightly change the loop iteration or change the naming of the registers. And what this looks like is if you go to access, let's say, register R1, there's a register, sort of a architectural enabled register called the rotating register base, or RRB here, which has a value that gets added to this, and it's modulo arithmetic, so it rolls around at the end, and that points to different locations in the physical register file. Oh, this is pretty cool. So what we're going to do is every single time we come to a new loop iteration, we are going to change the RRB, and it's going to point at a different set of registers. And we can actually effectively software pipeline just by using this one feature. So here we have the same code sequence we had from last lecture. So it was the previous code example. And if we recall, when we unrolled all of this, what we ended up with was a load, an add, a store. We'll talk about this in a second. This was kind of the key thing we were trying to execute. And if we have to unroll this, we basically had to unroll the code and then look at the dependencies. So let's look at the dependencies here. Well, dependencies that we're going to have is this load writes F1, or the floating point register F1 here. And we know that this is actually going to want to get read. Let's say the latency on this is 1, 2, 3 cycles, and it doesn't get read till here. Likewise, this add here computes P10, and the add, let's say, is a floating point add, has some long latency, and down here is when it's ready into the store. So on something like a Itanium with a rotating register file, we don't actually generate all this code. Instead, we generate one instruction, this, which is going to take care of our epilogue, our prologue, our epilogue, and the main loop. And what we're going to do is we encode the distance in register numbers between these two values here. So what this means is if this writes F1 and 1, 2, 3 loop iterations in the future want to read that value, we encode that here with a register number that is that number off. And then likewise here, so this would be F1 to F4 because it's off by 3. And here, this writes F5. And we know this wants to be read 1, 2, 3, 4 later. So we encode it with a register number that's 4 into the future. And now we're going to talk about this instruction here. So what this is going to do is it's going to change the rotating register base number, or the RRB, and it's going to bump it by 1. So we can basically just keep branching to itself here. And each time we do it, all the registers are going to change names. So by the time this is ready, or by the time the load is ready here, these other values will have sort of caught up with it, and where the physical register that they're actually going to look at will now point to the correct location. So we can effectively encode into one instruction here all of this, including the prologue and the epilogue, using this rotating register file. OK, so last slide of today. Why do I think Itanium, I think we can pretty confidently say, failed? I actually don't think it was a lot of the ideas. I think a lot of it had to do with the implementation. So first off, if you tie the hands of the microarchitect, they're going to scream. So IA64 added a lot of architectural, big A architecture, or ISA level features in order to get a lot of the speculative parallelism. And a lot of that stuff was implemented and talked about, but never actually built in real processor. So people didn't go through the effort until basically the first Itanium to try to implement some of these things. And they didn't all mix well together. And they added a lot of state, and they added a lot of complexity to the processor. So we have ALAT, full predication, or almost full predication, rotating register files, to name a few. This really complex bundling sequence, that's probably one of the hardest to decode instruction sets in the world. Very, very challenging. And this was a big challenge. And it tied the hands of the microarchitect. And the microarchitect couldn't make decisions. So a good example of this, and a funny story here, is that after the DEC Alpha employees, Digital Equipment Corporation employees, left DEC and were sort of assumed into a part of Intel, that same team that used to build out-of-order alpha processors went on to go build sort of the next generation of an Itanium processor. And what they said is they went to go look at the Itanium processor, and they're like, wow, this is really complicated. It took them much more complicated than alpha. And then they said, oh, well, we could probably do better if we just built an out-of-order superscalar, took apart all of the instructions, took apart all the dependencies, poured that data into what was effectively an alpha out-of-order superscalar core, and then execute it. And what was funny is if you go look at this is like all the people, you can sit there and just bang your head because you did all of this work and added all of this architectural state to allow the compiler to do all this work, and then they just wanted to undo it all. I mean, they did this because they wanted performance, but then they wanted to undo all of the sort of state and all of this hard work the compiler did and just redo it all dynamically because they thought they could get better performance. They probably could have. It probably was a good idea, but what's kind of funny there is you built an instruction set that had one microarchitecture in mind, basically an in-order architecture, and then all of a sudden people are thinking about building out-of-order variants of it. And it sort of throws everything you had before away, or all these notions sort of went away. So it's just a funny story there that people tried to build out-of-order versions. They ultimately did not end up doing that. That same team decided it was basically too hard, mostly due to predicate registers and sort of how to bypass predicate registers of out-of-order things. And I think they ultimately ended up not doing that, or they definitely ended up not doing that. And that's what's sort of known now as the Wachusett or excuse me, not the Wachusett. It's known as the Tukwila processor from Intel. Other couple of problems here. First implementation at a very low clock rate, so your first one out the gate just was not very good. This sort of hurt. And it's hard to build these things. They're wide. The speed demons versus the sort of brainiacs. This is this question of do you want to go wide or do you want to go long and narrow? Long and narrow was doing OK at the time. Big code size bloat. Fundamentally did not solve all of the dynamic scheduling problems that out-of-order superscalar could get at. So for instance, branching or changing your instruction schedule based on whether a load hit or missed in the cache, they couldn't do. Big compiler complexity, you needed profiling and not everyone wanted to profile. There was also just not that much in static instruction level parallelism in all programs, so the compiler couldn't necessarily find all the parallelism or wasn't there statically. And if you're going for a compiler-only approach, you need to be able to do that. And then this is what really killed it here is the people did go build these more complex out-of-order superscalars. So at the time, there was this big discussion, can we build more complex out-of-order superscalars? And people said, no, those are too hard. They're too hard to build. They cost too much. We don't know how to solve all these problems. So instead, we'll try to build something simpler and push a lot of complexity into the compiler. Well, there was money behind this question. So people went and did build these complex out-of-order superscalars. And that's what we're basically still using today in our sort of desktop processors. We have out-of-order superscalars today. And then finally, the last big one here, AMD 64 happened. What is AMD 64? Well, it's a 64-bit extension to x86. AMD originally did this. Intel, after sort of dragging their feet for a couple years on this, finally decided, oh, we're gonna use that because people wanted this. People wanted code compatibility with the ability to do 64-bit sort of wider, both arithmetic operations and wider addressing, so more amounts of memory. And 64 bits is a lot of memory. So AMD originally came up with this. This is now known as, I believe, EMT64 or Intel 64, not to be confused with IA64. That's what Intel calls now the 64-bit extension to x86. And now Intel's building those processors too. So everyone has sort of jumped on that. And Intel's kind of de-emphasized Itanium now in the Itanium instruction set. And instead, we're basically sticking with IA64 in this instruction, IA32, the 32-bit x86 with extensions to 64-bit, and that's taken over the workstation market. And what's kind of funny here is this processor was really designed to kill or unify all of the workstation vendors together under one processor that was going to beat them all. And it did its goal to some extent. Because this processor was coming around, either companies went out of business or they jumped on the IA64 bandwagon and decided they were going to take that on. But what replaced all of the different little variants of processors that were in workstations, so Spark, PA Riskin for HP, SGI's sort of MIPS processors, I already say Spark, yeah, all these sort of other different things, and Power by IBM. Power's still around, but a lot of the other ones sort of died through attrition or moved on to were supposed to move on to IA64, but IA64 did not end up winning this. Instead, we replaced it with 64-bit x86 processors. So it sort of did its job. It killed the workstation processors, but replaced it with not itself. It ended up replacing it with something else. Anyway, we're gonna stop here for today, and we'll talk more next lecture.